Good evening, welcome to another episode, and today we will be discussing divisibility tests. Alright, so first of all, let's get some definitions out of the way. The first definition is that of congruence modulo n. So we say that two integers a and b are said to be congruent mod n if and only if n divides a minus b. And the second definition is that of divisibility itself. So we say that n divides a minus b if a minus b can be represented in a form n times some constant c. So for example, 12 can be written as 4 times 3, and we say that 4 divides 12. Quite apparent and quite obvious, I would presume. Okay, and the next definition is that of the representation of natural numbers. So we have that any natural number can be represented in successive powers of 10. So for example, the number 1, 2, 3, 4 can be represented as 1 into 10 to the power of 3 plus 2 into 10 to the power of 2 plus 3 into 10 to the power of 1 plus 4. And in general, for an n-digit number, where n is the number of digits, we have this representation. And I would encourage you to keep these definitions in mind as we move on to our divisibility test. So let's get started. Okay, so let's begin with our first divisibility test, which is divisibility by 3. The definitions should appear on your screen right about now. Please do keep those in mind as we go through our proof. Okay, so let's begin. So in order to answer this question, we need to look at solving or at least simplifying this equation, mod 3. So recall that any number can be written in this form, and we're trying to solve for when a particular natural number is congruent to 0 mod 3. Okay, so we can begin by making a small observation, which is that 10 is congruent to 1 mod 3. This is because 10 minus 1, which is 9, is clearly divisible by 3. And we can use this to our advantage. So for example, we can take 10 squared, which is congruent to 10 into 1 mod 3. But again, notice that 10 is congruent to 1 mod 3. So we can just substitute 1 over here, and we'll just be left with 1. And we can now conclude that 10 squared is also congruent to 1 mod 3. And in general, for any power of 10, so 10 to the power of a will always be congruent to 1 mod 3. And this is really helpful because now we can reduce this expression modulo 3 and replace all of the 10s in this equation with 1, and we'll simply be left with the numbers of the digits themselves. So for example, we'll be left in this expression with 10 dn minus 1 plus dn minus 2 plus d1 plus d0 is congruent to 0 mod 3. And from this we can conclude that a number will be divisible by 3 if and only if the sum of its digits is equal to a number which is divisible by 3. Alright, now let's move on to our next divisibility test. Alright, so let's move on to our next divisibility test, which is answering the question, when is a number divisible by 4? And we have the same setup over here, except now we are working mod 4, and we will proceed to use the same trick as before. So notice that 10 is congruent to 2 mod 4, or in other words, the remainder when 10 is divided by 4 is equal to 2. And now notice that 10 squared is equal to 10 into 2 mod 4, but that is simply equal to 4 mod 4. But we know that 4 is congruent to 0 mod 4. And in general, we have that 10 to the power of a is congruent to 0 mod 4 for all a greater than or equal to 2. So with that in mind, we can now make a reduction from all of these digits up to and including d squared, d sub 2 sorry, will be equal to 0 mod 4. So let's make that a bit more apparent. So let's look at our equation. We have 10n minus 1 dn minus 1 plus 10n minus 2 dn minus 2 plus all the way till 10 squared d sub 2 plus 10 d sub 1 plus d sub 0. And as I said before, that any power of 10 greater than 2 is congruent to 0 mod 4. So all of these digits will then be reduced to 0 mod 4, and we'll be only concerned with this expression right over here, and we'll be left with 10 d1 d sub 1 plus d sub 0 is congruent to 0 mod 4. And now we just have to look at the final two digits, and if the final two digits equal a number which is divisible by 4, then the entire number will also be divisible by 4. So let's look at okay, so let's say we wanted to look at this number 1, 2, 3, 7, 8, 9, 4, 6, 24. Okay, and notice that we just have to look at the final two digits of this number, and since 24 is divisible by 4, we can conclude that this entire number over here will also be divisible by 4. Okay, let's move on to our next divisibility test. Move on to our next divisibility test, which is divisibility by 11. This is going to be slightly more technical, so just bear with me. So the first thing that we need to now look at is we're going to rewrite our number in terms of its digits and the powers of 10 as we did before, but I'm going to make a slight change to our equation. I'm going to write the last digit first. So we're going to have d naught plus 10 d1 plus 10 squared d2 plus 10 cubed d sub 3 and all the way till d 10 to the power of n minus 1 dn minus 1, and we need to answer the question, when is this number congruent to 0 mod 11. Okay, so we'll begin by making a small observation as before, that 10 is congruent to negative 1 mod 11. Why is that the case? Because 10 plus 1 or 10 minus 1 is equal to 11, and 11 divides itself, so we have that 10 is congruent to minus 1 mod 11. And now we can again start squaring and see what happens. So we have 10 squared is congruent to 1 mod 11, and 10 cubed is congruent to, again, -1 mod 11. And if you notice, a pattern begins to emerge over here, that whenever 10 is to an even power, we have 1, it is equal to 1, and whenever 10 is to an odd power, we have -1 mod 11. So let's formalize this. We have 10 to the power of a is congruent to -1 mod 11 to the power of a. And again, we can now use this piece of information to our advantage in solving this equation. Okay, so when we left off, we had come up with this lemma which states that 10 to the power of a is congruent to -1 to the power of a mod 11. And we can now reduce this equation by using this lemma. So 10 to the power of 0 is simply going to be 1 by definition, d naught, plus 10 to the power of 1 is -1, so we have -1 d1. 10 squared is again 1, so we have +1 d squared, -1 d cubed, and +1 d4, all the way up till -1 to the power of n minus 1 dn minus 1 is congruent to 0 mod 11. So now we have reduced this equation to just a sequence of adding the digits by 1 and -1, and that will give us a really good way of checking if a number is divisible by 11. Okay, let's have a small example of this to clarify this. So this is an example of divisibility by 11, and we're trying to answer the question, is 37,785 divisible by 11? Now, you could go about this the regular way by long division and check, but I think this is a really good way of seeing how by reduction modulo 11 we can perform this calculation much faster. So let's begin. So we need to answer the question, is 37785 congruent to 0 mod 11, right? And now we can begin to use this equation over here, and we will first of all take the 0th digit, which is 5, and multiply that with 1. Then we will take the 8th digit, which is, and multiply that with -1. Then we will take the 7th digit times 1 plus. Now we just need to add this expression together, which is going to equal 5 plus 8, 5 minus 8 plus 7 minus 7 plus 3. And this is going to cancel. This is minus 8 plus 3 is 5, and we're left with 5 minus 5, which is equal to 0. And from that we can conclude that since this number 0 is congruent to 0 mod 11, then this expression over here, I mean this number over here, will also be divisible by 11. Alright, hope that helped.